Hi. So, as promised, we will talk about this quantity called the circulation, which is defined as U is a velocity field as before, and there is a dot product in between. It's important to, so this seems like a line integral, a closed line integral, since we have written it like this. Yeah. Now, the line L, the line is a closed contour moving with the fluid. This is important to keep in mind. As if the contour is frozen into the fluid. Okay? And so, it is in this particular situation that this definition of circulation is valid. And the next thing I want to say is that this entire discussion is valid for incompressible, meaning the divergence of U is 0, right. Inviscid, meaning the viscosity is negligible. Barotropic, we will, maybe I've said this earlier, but essentially saying that the pressure P is a function of rho. Fluids under the influence of conservative body forces. Okay, body forces are conservative. In other words, if there is a body force G, it can be expressed as the gradient of a scalar potential phi. With this, just want to emphasize once again here, this potential phi refers to the potential which describes the body force. It's a gravitational potential, it's not the velocity potential. Okay, we use the same symbol for both, so I figured I would emphasize this. So, at any rate, all of our discussion which we are going to have right now takes all these restrictions into account, and the definition of circulation that we will be talking about is this, where this dl is a closed contour that is moving with the fluid, in some sense frozen into the fluid, right. So, with those caveats, let us move ahead. And so, this is the definition of the circulation that we just said. The circulation K is this. And so, what we do now is the Euler equation that we have seen earlier. Instead of writing it in the lab frame, we write it in the Lagrangian frame. It is a little more convenient, because you see this contour that we are talking about is moving with the fluid. So, naturally it makes sense to be sitting on top of a fluid parcel, so that this contour is not changing for you. Okay. You are sitting on the top of the fluid parcel and you are watching stuff go by. So, you write down F equals ma in that frame, so that defining the contour is also easier. You are sitting on top of the fluid parcel and the contour is not changing as far as you are concerned. Okay, it is still a closed contour. So, the Euler equation using the material derivative is this, and from the definition of K, this definition, you do this operation U dot dl all through the equation. And this connection, as you might already have guessed, this connection is made using Stokes' theorem. You relate the line integral to the surface integral using the curl, right. I sometimes write the area element as ds, sometimes I write it as dA. I am hoping that the context will make it clear what I am talking about. In this case anyway, we were not yet talking about the surface integral. We just do a line integral of all terms here, right. Before that, the du dt I write down as the line integral of du dt is I dot it like so. There is this component and then there is this component. In other words, the circulation can change because the velocity itself is changing, or the line element is being stretched or compressed. It's moving with the fluid, but you're allowing for the fact that the shape might change, and that is this term here. Okay, so that is dk dt on the left hand side, and on the right hand side you have, remember, you have the gravitational potential and you have the gradient of p, and so you do the line integral again because that's what we were doing to all the terms of the equation, and you have d phi gradient of phi dot dl, and this is just a perfect differential, and we got this is a perfect differential because you see there's already a gradient of p, yeah, and because we want to retain just this term on the left hand side, this one, this fellow, it goes over to the right hand side, right? So that's where you get this. Yeah. So as such, there's nothing, there's no mystery. It's just a simple rearrangement of terms, and the important thing here is that each term is a perfect differential. Okay, you see there's a gradient of phi, and it's dotted with dl, so that becomes a perfect differential. This is already a perfect differential by definition, and I claim that this is also a perfect differential, this term. Why is that? D over dt of dl is a u, right? So it's a half u squared. So therefore the integral of any perfect differential along a closed path is 0. Okay, that's the whole point of a perfect differential. It's you integrate it around a closed path, and the integration is 0, and which means that dk dt is equal to 0. In other words, okay, by the way, before saying that, you remember, just wanted to emphasize that this whole thing was you could write it started from the vorticity equation, and you could write this down. You could write down the vorticity equation in this form only because the gradient of rho and gradient of p are parallel, which is true only for barotropic fluids. I want to emphasize this once again. Okay, so what we've now said is that the time rate of change of vorticity is 0. In other words, the circulation, this quantity k is conserved, right? So circulation is conserved in an inviscid barotropic fluid. Also importantly, it's true only for situations where either the body force is absent or the body forces can be described using a conservative potential. Okay, that's not written here, but I want you to keep that in mind firmly. So if the circulation was 0 to begin with, it will always remain that way, right? So now here's a bit of a conundrum. You must have, water, right? There's no, before I launch on this description, on this example, I just want to say that there's no such thing as a perfectly inviscid fluid. These are all approximations. But nonetheless, water, you think of water as a pretty much inviscid fluid. The viscosity is not very high, especially in comparison to a fluid like, say, honey, right? Now, we are saying that the circulation is conserved, vorticity is conserved, right? In other words, if there are no vortices to begin with, vorticity cannot be generated. But you must have noticed, you take a hose and of water, and the flow coming out of that hose is fairly laminar. It's not a very turbulent flow, so that the streamlines are nice and well behaved. There's no evidence of vortices, right? Now you take a hose of water so that the flow out, the water flowing out of the pipe is fairly laminar, and you aim it at a wall, right? And what happens at the wall? All hell breaks loose, right? There's a lot of vorticity, and lots of these vortices are generated. So what gives? Right? How come vorticity is being generated, at the wall, and so that seems to violate this, right? It seems to be generating vorticity from nothing. The answer to that lies in the fact that there are very large velocity gradients that are being generated right at the wall. Okay, in other words, the fluid is coming to an abrupt halt at the wall, and so the gradients of u and so on and so forth are being there are very, very large gradients of velocity that are being generated right at the wall. And as we will see once we start talking about the Navier-Stokes equation, we will see that there is no such thing as well, I said that in the beginning, there is no such thing as an inviscid fluid. While viscosity might well not be important in the bulk flow, it becomes important in places where the gradients of the velocity are large. This is because the kinds of terms that we will see when we discuss the Navier-Stokes equation in a little bit, the viscosity appears in this combination like that. Okay. So, the del square is a second derivative. Okay. So, mu might well be very small, the coefficient of viscosity might well be very small. Okay. But when the gradient of velocity is large, as it would be when the water is coming to an abrupt halt, to say nothing of the second gradient or the second derivative, this one, the second derivative is even larger. So, as a result of the fact that the second derivative is large, the multiplication of these two, this assumes importance. So, this term, which is essentially the only combination in which the viscosity appears in the momentum equation, this term assumes importance even though mu is small in the bulk of the fluid. This term assumes importance at boundary layers, such as the one where the water jet is mating the wall. Okay. In that thin boundary where velocity is going to 0 over a very small thickness. So, du dx, so to speak, is large, and d square u dx square, which is what this is, becomes even larger. So, the multiplication of these two terms assumes importance. And so, viscosity, one of the basic things that's implicit in Kelvin's vorticity theorem, which is that of an inviscid fluid, this gets broken down even for water. That's why vortices can be generated. Okay. So, this is again a very simple explanation to an apparent conundrum, and but nonetheless this is the general statement. If vorticity is 0, it will always remain that way. If on the other hand there is some vorticity, it remains that way also. Okay. Now we come to this, as was the case with the Bernoulli constant. We used it to demonstrate a couple of interesting real life examples. Here is a real life example that I would like to illustrate that uses the concept of circulation, if not the concept of Kelvin's vorticity theorem, at least. So, you recall the potential flow around a cylinder, you recall this. This is what the flow looked like, right? Yeah, and around a ball, say, yeah, and so like so with the, and by the time you reach it, you're very far away, it's as good as straight. Now there's no circulation here. If on top of this I impose, just because I say so, okay, let me impose a circulation. In other words, let me impose a streamline that looks like this. So bear with me, I'll tell you why. Okay, let me impose a circulation on top of this. I add this kind of a circulation to the flow by hand. Okay, in other words, I add a k. This is a non-zero k. The fact that I've added this kind of circulation to the flow. Yeah. In this case, the streamlines now start looking like this. In other words, the streamlines, because this circulation adds here and subtracts here. You see here, down here, it's this streamline is opposite to the direction of this streamline, whereas here up here the streamline is in the same direction of this streamline, right? So it adds up here and subtracts down here. So as a consequence, the streamlines now start looking like this, where they are more densely packed at the top and sparsely at the bottom. Okay. Now what's this saying? What's the density of streamlines? What does it say? In other words, the velocity is higher here, right? So it's So as a result of the fact that there is lower velocity here as opposed to here, the pressure below will be larger than the pressure above. Yeah? In other words, there is a net upward force in this kind of a situation, right? Where, what kind of a situation are we talking about? One where I have arbitrarily added a circulation of this kind to a potential flow, okay? And I'll tell you why this is useful in a minute, but the bottom line is that in this kind of a situation, this body will experience a net upward force. So now I've mentioned the word spinning ball. This obviously has to do with the fact that I've included a circulation here, right? Now, although we are talking about an inviscid flow, right? Let's for a moment think about a real life situation where the viscosity is not negligible. So let's think about a situation where the ball is spinning in this direction, right? I impart a spin to the ball. Okay, this ball is spinning in this direction. Now viscosity is all about sticking a fluid, right? So the fluid sticks here, and because the ball is spinning, it tends to drag the fluid along with it. Yeah. So the fact that there's viscosity generates circulation. So it's the same thing, in effect it's the same thing as adding circulation by hand. Okay. So if the ball is spinning, it generates this kind of circulation. If you generate that kind of circulation, well then you have this kind of situation where the velocity the velocity of air above is smaller than the velocity of air above is larger than the velocity below, and therefore the pressure below is larger than the pressure above, and therefore the ball experiences a lift. Okay? The direction of force is perpendicular. The direction of the lift is perpendicular to the rotation axis. The rotation axis, as you know, is inward like this into the plane, and as well as the local flow. Okay, this is very similar to Lorentz forces, which are these kinds of very similar to that. Okay, in electrodynamics. So this kind of thing is used by tennis players when they impart a topspin in the ball. You know, I mean, when a tennis player wants to make sure that the ball does not go outside of the court, right? He or she imparts a topspin. Okay, so when they impart a topspin like so, what happens is, because of this Magnus effect, there's a downward force on the ball. So the ball kind of curves and it falls within the baseline and it does not go out. And that's because there's a downward force and there's a curve. And it's the same thing with a cricket spinner, and this is not as common. Mostly it's used by leg spinners, wrist spinners. And what happens is when the wrist spinner gives a vicious spin to the ball, there's often a dip. Okay, and that deceives the batsman. And this is what the Magnus force is all about. This is not swing. Okay, this is not the swing effect that fast bowlers use, and that's much more complicated. Okay, swing is when there's a sideways movement. Here, this is a case where there's a downward or upward. In this case, the direction of the force is upward, but and in tennis, you either give a topspin or you give a slice. Okay, when you give a slice, you're doing this, and then there's an upward force, and when you give a topspin, there's a downward force. Okay, you can work out the direction of the forces, and it's essentially this, the Magnus effect. Before we go on, I figured, so we will be going on to discuss viscosity from now on, and so all of this stuff that we talked about right now had to do with inviscid fluids, incompressible fluids, also subject to body forces that could be described by a conservative potential. Also, when we're talking about circulation and conservation of circulation, we were also talking about barotropic fluids. So this kind of wraps up this section of the course, and from now on we will start talking about viscosity. We will pay some attention to viscosity, and we will introduce the Navier-Stokes equation. And as you will see, we have already seen the Navier-Stokes equation earlier. We specialized from there on to the Euler equation where viscosity was 0, but we had actually seen the Navier-Stokes equation in a slightly different guise because we were already talking about shear forces, shear stresses, and shear stresses intrinsically have to do with viscosity. So we will just introduce the Navier-Stokes equation in a minute, and so for the time being we will close this discussion here. Thank you.